Pre-calculus. This video is going to talk about the applications for sinusoid functions or sinusoidal functions. So we already talked about a little bit at the beginning of the unit about how a sine graph models certain things in real life. So that is what this video is going to focus on. So the first thing we're going to talk about is frequency. Frequency is the number of cycles the function completes in a 1-unit interval. Mathematically speaking, it is the reciprocal of the period. So if I'm talking about the parent function for sine, and the period is 2 pi in radians, that means that the frequency would be 1 over 2 pi. All right, so how can we write a sinusoidal function using frequency? So we're going to talk about music because music frequency is something that most people are familiar with. Music and sound have sound waves and they take on a sine pattern. So let's talk about this idea in physics real quick. Frequency is measured in hertz or oscillations per second. Remember we talked about the sine function oscillating back and forth. So that's what that's going to entail. For example, the number of sound waves passing a point A in 1 second would be the wave's frequency. So that is kind of how we need to think about this stuff. So musical notes are classified by frequency. In the equal tempered scale, middle C has a frequency of 262 hertz. We're going to use this information and the information over here to write an equation for a sine function that can be used to model the initial behavior of the sound wave associated with middle C having an amplitude of 0.2. Okay, so don't overthink this. We are still writing a sine function, and any number in front of it is going to be considered the amplitude. And any number right after it is going to be dividing the period, okay? And then, of course, we won't have an x value or a theta value here. This will be in terms of time. So this is the equation we're shooting for here. This is a general function or a general form where y is a function of time. Okay. So having said that, we need to figure out what the measure of A is, and we need to figure out what the measure of B is, and that's all we need to do for this. So the amplitude is given to you at 0.2. We do need to find the period for this particular equation. So that's where the frequency comes in. Remember, I already told you that the frequency is the reciprocal of the period. So that means that if I'm dealing with the sine function, that means that I've got 2 pi would normally be divided by whatever this value is in here. So 2 pi divided by b, we don't know it, would be equal to the reciprocal of the frequency. Since the frequency is equal to the reciprocal of the period's equal to the reciprocal of the frequency. So now I'm just going to cross multiply and I'll be done. So b times 1 is b, 262 times 2 is going to be 524. Don't forget your pi. And that's all we have to do. That is our equation. We are not going to delve any deeper into it than that. Okay, the next thing we want to look at is this amusement park problem. So we have a position on a Ferris wheel. We're going to focus on this position right here, and it's at the center. And of course, it is going to move over t seconds as shown below. Now, when we're looking at these pictures, this is like I'm standing here and looking at it this way. So that's what these views are. So you can see this person that's right here. So at y equals 0, No time has passed. Well, then, as there's movement this way, when it gets up about halfway here, 2 seconds have passed. When it gets all the way to the top, 3.75 seconds have passed. And then as it makes its way back down into the same position it was in here, then we have another 2 seconds passing, or sorry, a little bit under 2 seconds passing to give me a time at 5.5. All right, so let's analyze what's going on here. I know this can get a little weird. Okay, but I want you to think about this. Half of all the way around the circle. So right here, y is equal to 0, but as it moves up, y is equal to 14, and then at the top, y is equal to 19, okay, that distance there. All right, so when we're answering questions about this, A, find the time t it takes for the cart to return to y equals 0 during its initial spin. So for part A, we want to know how long it takes from here all the way around to there again. How long does it take to move through half of the Ferris wheel? Well, at y equals 0, t equals 0. At y equals 14, t equals 2. At y equals 19, t equals 3.75. Then as it makes its way back down to y equals 14, see, the time that has passed is 5.5. So that means I need to know what this time is right here. Okay? Well, if from y equals 0 up to 14 is 2 seconds, then it stands to reason that it would take 2 more seconds in that direction. So for part A, the time it would take would be 5.5 plus 2 seconds. So that would be 7.5 seconds. Okay, now we're going to look at B. Find the period of the Ferris wheel. Okay, remember, the period is how long it takes to go all the way around. So if half of the Ferris wheel, it takes it 7.5 seconds, then the period is going to be equal to 7.5 times 2, which is 15 seconds. C, we are going to sketch the graph representing the position of the passenger cart over one period. Okay, this is a sine function. So I am going to draw this right here. We start at 0, 0. How do you know, Miss Griggs? Well, at y equals 0, t equals 0. Are you with me? So this is the y-axis and this is time right here. All right, so as time passes, I can look at my curve here. So I am just going to think about, okay, when t equals 2, y is at 14. Okay, so I'm going to call that 14. Actually, I don't want to do that yet because we really don't need to. Okay, so as time passes, as we go through 2, we get y equals 14. Okay, so as it curves up, that's what's happening. And then once it gets to a peak, that's at 19 and 3.75. So basically what's happening, I wish I'd done a better job with that. Let's redo it. Okay, let's do this. It's easier to do it this way and just label it. Okay, so at a specific time, t of 2, 14, at the peak up here, it's 3.75, 19, and then as it scooches back down, it's going to be 5.5 and 14. And then once it reaches here, we know that that takes 7.5 seconds. So that is going to be 0 and 7.5. And then as it scooches back around, this is the top half of the circle right here. Okay? So what I am looking at here is this. I'm looking at this. That's what I've taken care of so far right here. Okay, so as we move down, notice that we're dipping underneath the x-axis. That means the x values are going to be negative. So once we get here, but time continues to pass. So it passes at the same intervals that it's passing up here above the x-axis. So as I continue down to this value, it will be negative 14, but how many seconds does that take? It takes another 2 seconds, so 9.5 seconds. And then we peak here, that's at negative 19, and how many more seconds have passed? Well, 1.75 more seconds have passed, so this is 11.25. And then we do this again, and that's negative 14. And this would be 13 seconds, and then right here, that would be 15 seconds and 0. And I wrote this one wrong. Sorry, kids. Oh, I was afraid that was gonna happen. I'll just fix it. 7.50. Groovy. That's why I'm doing this for you and not making you do it by yourself. All right, write a sinusoidal function that models the position of the passenger cart as a function of time. Okay, so we need to consider our sine equation. This should not be too terrible. Okay, so the amplitude. Well, the amplitude is from here to here, okay, and it would be 19 because there's 0 and there's 19 right there. So we have 19 sine. Okay, we need to consider the period. Well, the period of the parent function is 2 pi. And we know that it takes 15 seconds to go all the way around, right? So we know that this is going to be divided by 15. And then it's a function of time. Easy peasy, lemon squeezy. That's something you use sine for. Okay, another thing we use sine for. We use them for tides because as the tide comes in and as it goes out, that can be measured by this. It comes in, it goes out, it comes in, it goes out, just like that. All right, so for this particular problem, we need to switch our color here because we're going to be dealing with water. At low tide, the depth of water at a beach at a certain point is 4 feet. Okay, so here's the beach here. Here's the water. So at a certain point, it's 4 feet. At high tide, the depth at the same point rises to 12 feet. Okay, so the same point, now it's 12 feet. So if the tide can be modeled by a sinusoidal function, what would the amplitude of the equation be? Well, let's look at this. If this is 12 and this is 4, okay, we need to think about the fact that, think about this. That would be the difference between 12 and 4. So this right here would be 8. Sorry, I lost my bearings for a minute. So that's 8 feet. So you remember, you think about your amplitude as half of that. So 4 feet is going to be your amplitude. Easy peasy, lemon squeezy.